Hey everyone! Today we're going to be learning about semaphores. So, what is a semaphore? Well, a semaphore can be thought about as a data structure that is used to allow multiple concurrent processes that are trying to synchronously access a common resource to be able to do so without creating any conflicting problems. For example, if you have two processes, A and B, who are both trying to access the same resource, using semaphores will ensure that only A or B can use that resource one at a time while the other has to wait. For example, imagine a semaphore as a bodyguard at a club. This club has a limited capacity of 50 people, thus only 50 people are allowed to be in the club at a time. As a result, if the club is completely full, then people have to line up and wait outside the club, and those that are waiting the longest will get to enter the club once people who are inside the club leave on a first-come, first-served basis. In our example, the club represents the common resource, the people waiting represent the different processes, and the bodyguard represents the semaphore. The bodyguard, or the semaphore, determines whether or not the people, or the processes, are allowed to use the common resource, in this case, enter the club, in our example. In addition to this, once a certain amount of people leave the club, then the bodyguard or the semaphore then signals or basically allows the people that are waiting to go into the club again on a first come first served basis. So currently, the club has maximum capacity of 50 people, and there are currently 50 people inside the club. Thus, if there are any new processes that come, they have to wait because of the semaphore not allowing them to access the critical region. So now, as the number of people inside the club goes down to 49, then what happens is that the semaphore signals to the different processes that are waiting to then allow one more process to now enter the critical region. And in our example, that would mean that the person that came first would then get to now enter the club itself and have a good time. So now the total number of people in the club is back at 50, which is again the max capacity. Thus, no more processes can now enter the club. As a result, if there are any new processes that want to enter the critical region or the club, then they have to wait along with the other processes. And now, if there is if there are less people in the club, then the semaphore will signal them and let the processes that are waiting on a first come first served basis. So in our case, it would be the gentleman in the blue shirt would then next get to go into the club. This is why having semaphores is vital when you're trying to carry out synchronous operations, because semaphores can allow you to basically regulate and determine which amount of processes get to access a critical region at a specific time without ensuring that they're not getting into the way of each other. So now, when the number of people in the club goes back down to 49, then the gentleman in the blue is signaled by the semaphore, which is the bodyguard, to now enter the club and be able to use the critical region. So in our example, we used a max capacity of 50, so that 50 people can be in the club at one time, or 50 processes can be in the critical region at a time, but this number can vary depending on the implementation of a specific scenario. So this number could be 3, 5, 10, 15, whatever we want it to be. And in binary semaphores, this number is only able to be either maximum value of 1 and minimum value of 0, which we will get into a bit later on in this video. So a semaphore is made up of a int count variable as well as a queue, and the int count variable takes into consideration the number of processes that can enter a critical region at a time, and the queue type variable is basically needed in order to assure that if the critical region is already occupied and can't take in any more processes, then what happens is that the queue is where the new processes that want to use the common resource or the critical region are not able to. They are then put into the queue, in which they will be then served on a first come first served basis when a specific process is done using the critical region, and there's space for a new process to come into the critical region. So if we look at the semWait function, which again takes in a semaphore, then this function is called before a process enters the critical region, and it checks to see whether or not the critical region can take in any more new processes. That's why the count variable is decremented, and if we look here, we see that it says s.count less than 0. So if s.count is less than 0, that means that the critical region is already being occupied with enough processes, thus we cannot take in any more processes inside the critical region. Thus this new process that wants to use the critical region is then placed in the queue, in which it will then again be able to be served on a first come first served basis once the semSignal function is called. So now if we look at the semSignal function, which again takes in the semaphore, this semSignal function increments the semaphore count value, and the reason for that is because once a specific process is done using the critical region, it has to then increment this count variable, because it then allows the semaphore to know that, okay, now there is again enough processes that can enter the critical region, as one of the processes that was already there has already used that critical region. So now a process then gets removed from the queue, which wanted to use the which wanted to use the critical region before but wasn't able to, but now it can, because there's some space in the critical region that is available once this value had incremented, and that process is then placed on the ready list, where it will then again attempt to use the critical region. So there are two types of semaphores. There's binary semaphores and there's counting semaphores. The example with the club security guard represented a counting semaphore, as it allowed semaphores to take on any integer value, whereas with binary semaphores, the semaphore count value can only be 0 or 1. As a result, binary semaphores are mainly used when you want only a single thread or process to access a specific resource or critical region at a time. So if we look back at our club example, if the capacity of the club was 1, using a binary semaphore instead of a counting semaphore would be a better choice and would make more sense. So now let's look at an example problem based on the knowledge that we've just accumulated in the past 5 minutes. So it is the day of Halloween, and there are a lot of trick-or-treaters out on the loose. There are only 5 houses on Laker Street participating in this year's Halloween. Create an implementation using semaphores that allows Laker Street to serve a maximum of 5 trick-or-treaters at a time, while also keeping track of the total candy distributed. So in regards to the solution, the first thing we need to do is implement the variables. So the first variable is the number of houses that are available, and this is set to 5, and these are the total number of houses that are participating on Laker Street. Then we have the total number of candy that's distributed, which is the variable, which is the value that we need to track. And then we have another semaphore, which basically allows us to access the total candy that's being distributed, and the variable, which is total candy being distributed. And the reason for that is that we have a binary semaphore, because it allows us to allows each house to access that common resource, which is total candy distributed one at a time, so that we don't have multiple houses changing that value, and in our case multiple processes, which are going to be all the houses, changing that value at the same time, because then that wouldn't give a accurate value. So initially what we do is we have to first create a function called trick-or-treater, and this is a function that runs every time a trick-or-treater reaches a house and asks for candy. So first thing we have is that we run the semWait function on the houses available semaphore, and this remember decrements the houses available count value, because this is a semaphore, by 1, so then it makes it a 4, and that means that now we have 1 process inside the critical region, which is this, so we can have a maximum of 5 at a time, because there's only 5 houses that are participating in this year's Halloween. So then the get candy function gets called, and here here we have again the semweight function specifically for accessing the total candy distributed, and we want to be able to access the variable one at a time. That's why we have the semaphore, so that each house accesses this value one at a time and then signals when it's done using it, so that the next house can update this value as well, and so on. So this is how we would implement the solution to the problem that was mentioned in the previous slide. Alright, so that brings us to the end of this lecture. I hope you got to learn something new about semaphores today, and thank you for listening, and hope you have a great day.